Core Pure 1, 2022, A-Level Further Maths, Pearson Edexcel. Let's do this first question, free mark for being awake at some point during your A-Level Further Maths time in lessons 2 plus 3i, it's the conjugate. Now, to get the other roots, there's a few ways of doing this, but, I mean, you could just multiply all three roots together and you'll get minus 52. You'll get a minus because there's 3 of them here multiplying, so the 3 negatives essentially in the factorization will give you a negative. You can expand this out, obviously you get this, I squared is minus 1, obviously, divide by 4 and you get that, so that's the third root, just having called it alpha. And so solved completely, it's just minus 4, 2 plus 3i and 2 minus 3i. Determine the value of a, now this is the one attached to the z, so that will be the sum of the different ways of timesing two roots together, so alpha beta plus beta gamma plus alpha gamma, and that will be equal to a, because you've got pairs of things multiplying here, not triples, so you don't need to have a negative there. Of course, some stuff cancels here, and which is nice. You know alpha is minus 4, by the way, which also helps out a great deal. This you've already multiplied to make 13, so you have minus 4 times 2 plus minus 4 times 2, and then you put those together, you get a as minus 3. I think that's the quickest way of doing it. Show the roots in an diagram, bam, that's that. Question number 2. So we have this here, you could make a quick substitution if you wanted to, it's not really necessary. This factorizes to this, again you've got a calculator, so that's not even that necessary either. The two solutions are 9/8 and minus 1/8. Of course you can put the substitution back if you did it. You can square root, of course this square root doesn't work. You can square out this though and you get this, which I want to do a couple of things too. Firstly, it says it wants stuff rational, so we could rationalize this by timesing by root 2 over root 2. To get 3 root 2 over 4, I believe. And also, if you look at the definition of cosh x, which you should know because that's not in the formula book, I don't think, this is always positive, because this is positive, you add two positive things together, divide by 2. So the negative actually doesn't matter here. The formula book does give you this, which is what I'm going to use. You could use this to solve this equation here, but instead you could just put arc cosh on the other side and just put this in for the x according to this formula. And you'll end up with this. Sorry, this is a bit confusing because I've put x equals here, but it doesn't really matter. This x is just this here, so I'm going to put that in a couple of times. This squared is that, because that's literally what we square rooted to get this. So that's there, that makes 1/8 there, which is 1 over 2 root 2 when you square root. And then you can put these together, this times is to make root 2 over 4, I think, which adds together to make 4 root 2 over 4, which cancels to just make root 2. Root 2 is the same as 2 to the power half. Bring the half in front of the log, and you end up with that. There's a plus minus here stuck right at the very end, because notice when you again look at the cosh formula here, when you put in a positive value, let's just pretend x is 5. When you put in a 5 here, you're going to get e to the 5 plus e to the minus 5. Now what happens if you put in minus 5? Well, you get e to the minus 5 plus e to the 5, which is the same thing. Doesn't matter what order you add stuff in. And so whenever you have a solution, like a positive solution for x when you're solving a cosh equation, you can also have the negative one just because of the symmetry here. That means that it's the same thing. Good, so that will be the answer there. Question number 3 is a differential equation. This is so close to just immediately working with product rule. Like you could, it's almost just the reverse of product rule. It's not quite because there's a minus that's slightly wrong. So what we need to do is we need to divide by cos x to make this. And now, of course, we've got a function here attached to the y, so we can use an integrating factor where it's e to the integral of this function is our integrating factor, so e to the integral of tan. That's in the formula book. Tan integrates to log sec, which of course then you can cancel the e in the log to get sec. So if we times this entire thing by sec, theoretically we should end up with something quite good. And we do, because again, if you look in the formula booklet, the differential of sec is tan sec. So now this is sort of a backwards product rule thing. By the way, this cos went away because I times it by a sec. So this is the backwards of product rule, right? You've got y sec x, and if you differentiate y, you just get dy by dx, leave this alone. And if you differentiate sec, you get tan sec, with the y being left alone. So this works, integrate both sides, or just move this dx over to here, I guess. But yeah, just integrate this side over here, integrate this side to get this. We end up with this, of course, and we could maybe times everything by cos, I guess, to get rid of this sec. And we get y equals that thing there. If y is 3 when x is 0, so you put those in, and you very quickly work out that c is 5 over 2. Determine the smallest positive value for which y is 0. So, okay, well, let's put that c in, and let's set y to be 0. We can factorize out a cos, we can double everything to get rid of the fractions. Now this thing here is always positive because that is and that is, you add them together, you get a positive. So we're just looking for cos x to be 0, which first happens when x is pi over 2. Question number 3, method of differences. So split this log into log of this minus log of that. because now we have two things taking away, which means method difference is going to work really well. Just try putting some values in and see what happens. So if you put in the 2's, you get log of 3 minus log of 1 is our first two terms. If you put in a 3, you get log of 4 minus log of 2, and so on, all the way until you put in n minus 1. When you put in n minus 1, you get this. N minus 1 plus 1 is n minus 1 minus 1 is n minus 2, and then when you put in n, you get n plus 1 and n minus 1, of course. Now, this log cancels with this log, that's good. This one is going to cancel with the log to the 4 that's going to turn up next. This one's going to cancel with the log to the 5 that's going to turn up eventually. In fact, all of these will start cancelling all the way down with all of these. This one will cancel with the n minus 2 that came 2 before this one, so that goes away. And this one will also cancel with the n minus 1 that came before this one here, so that goes away. And we're left with this, this, and this. This doesn't matter because log 1 is 0, so we're just left with this, and this. Of course, this is a negative, so we can just divide, and these are positive, so we can times. So we're going to get this. And is that what they asked me to get? Yeah, it is good. Okay, so we're done. Hence, find the exact value of that. First thing to say is this 35, based on log laws, can be thrown down to the front, and because it's just a number, it can be thrown way out to the front here. So that's good to see. And okay, that's the first job. Then, of course, we can say we have a result from 2 to n, not from 51 to n. So we can say this sum is the same as going from 2 to 100, and then taking away the result from 2 to 50. I think, because we'll get all the terms there, then we'll take away all of them up to 50, and we'll just have the terms from 51 to 100 left over. Now, of course, we can just use the formula, right? We can just use the formula here. This sum equals when you put n is 100 into here, because we're going up to n is 100, and this one equals when you put n into 50 into there. Of course, we don't actually want to multiply any of these things out. What we want to do is maybe just halve the 50 and halve the 100 to make this, and then we can divide these two logs. The 35 obviously factorizes out. We can divide those two logs. This divided by this is 2. 2 times that is 202, and we end up with a nice answer that I think is correct. Question number 5 is about matrices. Show it's non-singular. Non-singular means determinant isn't 0. So, okay, let's work out the determinant. It's a times the determinant of these four, which is 6 minus 0. So that's the first bit. Then minus, always on this one, 2 times 4 minus 0. I've been very extra how I've written this, but it's okay. And then minus 3 times 2a minus 12. Tidy that up, you eventually get to this, I think, and of course that's not 0 for any value of a, so it's non-singular. Determine n inverse. Now, if you're fortunate enough to have done FP2, you might know a really cool method for doing this that involves eigenvalues and the Cayley-Hamilton theorem, which you should definitely do if you get a question like this in a paper just to flex. If you haven't done that, you're going to have to do this the standard way, which is first you do M transpose, then you replace all of these inputs with the determinant of the matrix that they're sort of looking at when you block off their row and column. So for example, we replace this A here with the determinant of these four, which is 6 minus 0, so that's just 6. We replace this 2 with the determinant of these four, the 2 and the minus 3 and the A and 2, which is 4 plus 3A. We replace this 4 with 2 times 0 minus 3 times 3, which is 9. And then, for example, this 2 would be replaced by the determinant of these 4, the 2 and the 4 and the 0, 2. You go all the way around to doing that. You can check that I've got that right if you want to. At this point, we use the magic matrix of signage, which is this. You just essentially, anywhere you see a positive, you keep it the same. Anywhere you see a negative, you change the signs and all those terms. So these become negatives, that becomes negative, that becomes negative, that becomes negative to get this. And then you're pretty much done. I think that's called the adjudicant matrix or something, ADJ. I can't remember what the actual word is. And yeah, you just put 1 over determinant there. We already worked out the determinant was 28, and that's the inverse matrix. Question 6, so partial fractions. We just need to make sure that if you've got a quadratic term on the bottom which can't be factorized, which it obviously can't be, at least not across the real numbers, we put a linear term on the top. So this term here is always 1 degree less than wherever's on the bottom, although you'll never have to do it with like a cubic or a quadratic or anything. At least I don't think so. But yeah, we have this. Of course, now we can just multiply across, we get this. And now if you set x to be minus 1, this all goes away immediately, and we get 5 here, so 5a equals whatever this does when you put minus 1 in there, which I believe is that. And now you can't actually input anything to make this go away, unless you tried to put in like 2i or whatever, which I don't think would be very helpful. So what you can do instead is just compare coefficients. So over here we've got 2x squared, and we've got 1x squared here, and we also have bx squared. So I think b just needs to be 1 to make your second x squared and match there. And then this, you've got a 6 here, you've got 4 here, so you need this to be a 2. C times 1 means just C needs to be 2. You can verify that also works for the x's, but I think you end up with this as our breakage, uppage of this thing here, which means, of course, when we're integrating this, we're just going to integrate this. The only trick to notice here, like this clearly just integrates to a log, which is fine. This nearly integrates to a log, but the derivative of this is 2x, which would be fine if it weren't for this plus 2, which just messes the f dashed over f setup you need for logs to be the integrals. So what we can do is we can just break up that 2 and put it somewhere else, like over here, because now this does integrate to a log. It integrates to half log of this, because you just need to get the 2x from somewhere. And now what does this integrate to? Well, you look in the formula book and you see this. So if a was 2, this would be 2 squared plus x squared. So if I just put a 2, I mean this 2, you can just put out the front and say it's 2 lots of this where a is 2. And I think we end up with that. Of course, there's some simplification that can happen here. You can put 2 and 0 in there, which is what I've done here. Bring the half up to the top here. 8 to the half is root 8, which is 2 root 2. Arctan is pi over 4. That's 0. That's log 2. Again, it's root 4 here, bringing that to the top. And that's 0. So I think we get that. We can times those two together, and we can divide by this 2 because it's taking away, which of course cancels those 2's. It's going to be 3 root 2 and then plus a quarter pi. And yeah, I think that's done. Question number 7, we are racing through this, which is nice. Z star is the conjugate. Again, for anyone who was actually awake during your complex number lessons, you'll know that. And then of course, if you just do this times this, you get this, which is this. It's to show that, so I'm just being very extra with the work. I've even put I squared here, which we all know is of course minus 1. We just put a plus there and we get a real number. Good. Given this, so that means this, we just worked out what that is, so we know that's 18. And this. Now z over z star is that. You can realize this by timesing by this. We know what the denominator gives us. It gives us this. The numerator is going to give us a squared plus 2 lots of abi plus bi squared, but bi squared is minus 1, so minus b squared. And yeah, that equals this thing here. Now there's a nice little trick here, which is that you've got a real part here and a complex part or an imaginary part here. Split this up in the same way. So split it up like this. So now we've got the real part here and the complex part here, which means this bit must be 7/9 and this bit must be 4 root 2 over 9. Now you know a squared plus b squared is 18, so you may as well put those in. To both, you can cancel the 9's here, and you eventually end up with this and this. And there's a bunch of ways to go from here, but I just chose to add these two things together, I think, to get this, and then divide by 2 square root to get that. And then you can just shove that result into there to get b is plus or minus root 2, I think. And now, okay, so what combination of things is actually allowed here? We know the answer is some form of plus minus 4 plus minus root 2i. Well, you look down here and you go, okay, well, this is positive, so either a and b are both positive or a and b are both negative. So I think the only options are those two things there, and we'll have the answer. Question number 8 is a very long question. It just starts with a very standard use of de Moivre's theorem. I don't know whether I ever pronounced his name right, but no one's ever corrected me. So we start with this. Choose n to be 1, just because we've got a 1 there, so it seems to make sense. Raise it to the power 6, and do a binomial expansion here. So the first time will just be z to the 6. Second term will be 6 choose 1, which is 6. Z to the power 5, and then 1 term of that. But that's going to cancel to make z to the power 4, so that would be quite cool. 6 choose 2 is 15. 4 lots of those, 2 lots of those, which again will cancel to make z to the 2. And you keep going. Eventually you end up with this. Of course, the coefficients are symmetrical. This one's interesting because when you take 3 lots of that and 3 lots of that, all the z's cancel. So you end up with that, and then you start ending up with negatives, and that's all fine, and we get this. There shouldn't be some dots there, sorry, I just forgot to delete those. Now what you do is you group together the 6 and the minus 6, the 4 and the minus 4, the 2 and the minus 2, and leave the 20 alone. You can write the minus 6 as this again, and of course when you look at this, you just look at this here, and you go, well, okay, this just equals 2 cos 6 theta, because n has become 6. So that's 2 cos 6 theta, that's 2 cos 4 theta, that's 2 cos 2 theta, the 2's can times by the 6 and the 15, and you end up with this. Divide everything by 2, and you get the result I think they wanted. So that's a nice 5 marks. There's a thing being modelled like this, with this. Cool, it's going to be rotated, they've given us in bold here, 180 degrees around the x-axis, not 360. So we're going to do pi over 2 at the front of our integral of y squared dx, I believe. The maximum height is 2, the maximum height is clearly here, where x is 0. So when x is 0, cos is 1, so h is 2 as well, so that's fine. Use integration, so again, it's going to be pi over 2 integral of y squared dx. So we're going to square this. H is 2, so that just squares to a 4, which can come out here to make a 2 pi. And then cos cubed is squared is cos to the 6. Now, a couple of things to happen here. Firstly, cos is an even function, so it's the same on the left-hand side of the y-axis as it is on the right. So instead of integrating between -4 and 4, I can just integrate between 0 and 4 and double the result. And the second thing, of course, is I can use this here. If I divide everything by 32, and then replace theta with x over 4, which would make this a 3 over 2x, and this just an x, wouldn't it? And this an x over 2. And then just put a 1 over 32 at the front, because I'm just going to divide everything by 32 to make this match with this. I think I eventually end up with this result. So the 1 over 32 at the front, exactly what I was saying going on there. And now this is just very easy to integrate, isn't it? I won't go over this in much detail. It feels so wrong to put 4 into all of these, but that's just what you have to do. The reason making this a 0 was quite a nice idea is because all of this goes away with zeros, because sine is 0 and that's 0, so that just all goes away. And you end up typing that into a calculator and getting this. Limitation, just always say, what if the curve doesn't actually reflect the shape of the thing? What if it's not suitable? That's just always the mark you can get for free. Question 9 is a weirdly short question for question 9. Firstly, it's improper because one of the limits of integration is infinity. Secondly, show that this is divergent. So we just need to be careful here to replace the infinity with a t and then send t to infinity. So set it up like this. Integrate cosh is, of course, sinh. And then put the t and put the 0 in, we get this. Now, sinh 0 is 0 if you think about the definition. I brought up the definition of cosh earlier. Sinh is the same, but with minuses here. Of course, this is just 0. And what happens to this when we put t, or when we send t to infinity? Well, that just goes to infinity. This goes to 0, but we just end up with infinity. So this whole function goes to infinity as t does, which means it's divergent. And that's, just make sure you actually set this kind of idea up, and you should be fine. Given this has real solutions, well, the obvious thing to do here is just divide by cosh to get this. Divide by 4, I guess, and then do arctanch. Look in the formula book, you get this. And I'm not actually so interested in this, but why I am interested in this, apparently this only works if mod of x is less than 1, so this will only work here if mod of p minus 4 is less than 1, which means p over 4 has to be between -1 and 1, times by 4, you get this, and that's the answer. Question number 10 is the last one to do here today, and it's about a second-order differential equation, and we have this thing swinging around. Show a particular solution is this. According to the examiner's report, a lot of people massively overcomplicate this. All you're being asked to do is shove this into here and show that it works. So take this thing here, derive it. It's a product, right? So you derive that and goes away, then you leave this alone and you derive that. Derive it again because we need this. So this derives to cos, right? But then there's another product to do here, which actually goes to a minus there. You can put those two things together. You can say the left-hand side is this plus 9 theta, but again, theta is this again. So that's the left-hand side, is what we just found, plus 9 lots of theta, which is this. This is just 3/4 this, which cancels with this, which gives you this, which is the right-hand side. And that's all they were asking you to do. Hence find the general solution of the differential equation. Well, the general solution is the particular integral, which we have, it's here, plus the complementary function. And to find the complementary function, we just ignore this bit over here and just set this to be 0. But then we can just set up the auxiliary equation and say just replace that with m squared, and this goes away because that's kind of the linear term, isn't it? And we just solve m squared plus 9 equals 0, which gives us m is plus minus 3i, and then we have to have memorized the idea that if you have complex solutions to your auxiliary equation, that means that you set theta to be this. That's the complementary function. You would always still have an e to the real part t out the front, but we don't have a real part, so I just haven't written that. So that's the complementary function. Of course, I've already said the general solution is the complementary function plus the particular integral. So we just do this plus this, which is our particular integral, and we'll have that. And now they give us some additional conditions. So we have this. We have theta is pi over 3 when t is 0, and also it's at rest. So that's obviously the velocity, but that's d theta by dt in this scenario. So that's also 0. And that's going to be helpful because, of course, we can use these two conditions. Theta is pi over 3, so put that in there. T is 0. When you put in t is 0, this goes away, and this goes away. So we just get a cos of 0 is 1, so we just get a is pi over 3 immediately. And then we can use this thing here to find b, because if we derive that, we get this. Just putting 3, I mean, you can follow on, it's fine, there's more product all over here, but that's okay. But we can set t to be 0 when d theta by dt is also 0, and when t is 0, that goes away, that goes away, that goes away, so we have this is just 1, so we have this, which means b is 0, which means our proper proper solution here with the stuff in it is this here, sorry, I just changed that to be this, got rid of the b bit, and replaced a as pi over 3. And now it says, given that what t is 10, find the angle. So just put t is 10 into here. Put it into a calculator, you get this. Now that means that it's over here, and the angle is minus 62, like minus 0.62 like this, or 62, which means the mark scheme was confusing. It said plus or minus that, but essentially, I think what it's saying is you can't really have a minus angle here. The calculator gives you a minus angle, but that just means it's angle 0.662, right? And we don't really care about negative angles, so we'll just use this. And yeah, the last part is given the true value is that. How close is it? Well, it's pretty close, so it's a decent model. And the very last bit, the differential equation, this, which is the one we've been dealing with the whole time, is forced harmonic motion. How do we make it simple harmonic motion? Well, simple harmonic motion just doesn't want a function over here. Simple harmonic motion just wants the d squared theta by dt squared to equal just a linear function in theta. So this just equals minus 9 theta, so it just wants it to be this. So we just get rid of this function. This function is causing it to be forced, so just get rid of it. That's the entire paper. Thanks for watching.